So we didn't have a homework last week for incremental view maintenance. This comes with guest lectures. But there is a homework for this week because this is my favorite topic, information inequalities and AGM bound and all the extensions. So yeah, there is a fun homework. And today is going to be a very unusual lecture about information inequalities. So be prepared for something that most of you probably don't know about.
Are you planning to cover the Immerman-Barty at any point in the course?
Yes. When we talk about the data log.
Great.
Because it's about recursion. All right, so ready to start? Let's go for it. So the goal for today is to discuss the AGM bound. Which is a mathematical formula. It's an elegant, very elegant mathematical formula that given a full conjunctive query and statistics on the database. Actually, these are quite boring statistics. They're just the cardinalities of the relations. So just the cardinality of the relations and a full conjunctive query. It gives us a formula that describes precisely the maximum cardinality of the output of the query. Very interesting formula. This can be used for cardinality estimation. This is something that we used in my group. But most excitement that it generated this line of work was the fact that some people about 10 or 15 years ago, they found a matching algorithm, an algorithm that can run in time that is guaranteed to be bounded by this formula, by the maximum size of the output. And this is in some sense optimal because you have to list the output of the query. So if you can run in time, which is guaranteed to be bounded by the maximum output, then you are in some sense optimal. One of the main inventors of this algorithm was Hank No, and he's going to give on Thursday the guest lecture on the worst case optimal joints. And today we're going to discuss the AGM bound and its extensions and the techniques that go into the AGM bound, which are entropic inequalities. Okay, yes.
Where does this fit in with Yanakakis?
What is he?
Like, where does this fit in with Yanakakis' algorithm?
Yeah, it's a very good question. So Yanakakis algorithm runs in linear time in the size of the input plus the size of the output. It only works for acyclic queries. If you are faced with a cyclic query, then you can do a tree decomposition, and then you need to focus on how. There are two parts. You need to compute the bags for each node of the tree, and then you can run Yanakakis on top of it. The worst case optimal joint refers how to compute those bags for which you have no other choice. There is no more Yanakakis algorithm that you can run there. Yeah. So for today, look for very intricate and very connected queries, although some examples will be acyclic. And when you see a cyclic Yanakakis, it's usually the winning strategy. But I will also illustrate with cyclic queries because this makes the AGM bound much clearer. Yes, Max.
Yanakakis runs in those are instance input and output, right?
Yes.
Whereas the AGM bound is not that.
Say again.
The AGM bound is not talking about instance output. It's talking about worst case.
Yes, it's a good observation. So the AGM bound does not talk about the output. It's a weakness, it's not a strength, because it runs in time which is proportional to the worst case output. The output may be much smaller, but the worst case optimal joint cannot guarantee that it will run in time that is proportional to the true output. It's a weakness. That's the state of the art. Good. So let's talk about the AGM bound, which is a form of cardinality estimation. How many people here know classical cardinality estimation, like a database textbook cardinality estimation? How many people know this? Okay, not that many. So I have 3 slides. Cardinality estimation 101, what everybody should know. So this is what every database system needs to implement. There are the input relations. These are stored in the database catalog. And for each input relation, the database maintains some statistics. How many tuples? How many distinct values do you have in each attribute? Maybe some histograms of these attributes. Small statistics. These statistics, they cannot be big. They have to be small. The task is, given a query, in general, any query, but to be honest, cardinality estimation, they actually can only handle full conjunctive queries. Beyond that, it's a big hack. So consider a full conjunctive query, select from where, yeah, with conjunctions, try to estimate the size and the number of tuples returned by this query. And I put estimate in quotation marks because it's not a very well-defined mathematical notion. But when you see it, you know it, okay? Yeah, we know that we can estimate it. Cardinality estimation has a huge number of applications, mostly in query optimization. The query optimizer needs to estimate the cardinalities of various intermediate results to decide if one plan is better than the other, and many other applications. So how do database systems do? Here is one slide. This is all you need to know. These are in standard textbooks from 20 years ago. So they estimate the size of a query by processing the query plan. It's not the only option, but it's one of them. Bottom up, start with selections which are done on the leaves. So selection, recall sigma means a selection of based on a predicate P. For each predicate, there is a selectivity factor, theta. For example, if the predicate says retrieve all records with zip code equals 98 something, then for zip code, you have a selectivity factor, maybe that's 0.0001, because you think how many zip codes there are, and there is means that a particular zip code represents a small fraction of the data. That fraction is something you know, or you get it from a histogram. So this selectivity factor is something that the systems know. But if you have more predicates on the relation, if you are lucky and have a two-dimensional histogram, you can use 2 predicates. If you are not lucky, then what systems do, they assume independence. They simply multiply those selectivities. You have a predicate on zip code and on city. Each of them has a selectivity, you just multiply them. Big mistake, because zip codes are correlated to cities, and it leads to huge underestimates of the cardinalities. Good, so this is for single predicate. What about joins? So here you need to pay a little bit attention. If the join is between R and S, what systems do, they start from the cardinality of R, and they think how many tuples can one tuple from R produce? Well, the average number of tuples are associated to a given B in S. That is the average degree of B in S. So the average number of C's for a given B. Yeah, this is the answer. The number of tuples in R times this average degree. They actually, systems don't store the average degree. They store the size of the number of distinct values of the attribute B. So the average degree is the size of the relation S divided by the number of distinct values. Yes.
This might be a dumb question, but why do you want the average degree instead of the worst case degree?
We will actually use the worst case degree towards the end of this lecture, but that gives you an upper bound. And this is where I'm heading, towards an upper bound. Database systems, they want an estimate.
Okay.
So for the estimate, it makes sense to take the average degree.
Okay.
Here is a typical issue that cardinality estimations face. There are two ways to estimate it. You can start from R multiply with the average degree, or start from S multiply with the average degree. It's not clear which one to take, not clear how to combine them. In this particular case, database systems, they always choose the minimum. There is actually a justification for this. It's called the preservation of values assumption. I'm not going to describe it, but by taking the minimum, you're essentially dividing by the maximum of the domains. And this is a standard textbook formula. This is what you will find in any database system. Okay, so this was cardinality estimation 101. So some comments. Cardinality estimation is known to be very hard. This is the Achilles heel of database systems. This is why they make errors. It became, again, a very hot research topic today, although it has been around for 50 years. Yes?
Sorry, when you say they make errors, like, do these just, I thought these just affect performance, they also affect the results of queries, or?
A good point. They affect the error of the estimate, which lead to wrong decisions of the query optimizer. The query result will be still correct, but the optimizer has chosen an inefficient plan. Somebody wants to enter? Is it locked?
Yeah.
Okay. So we just missed the textbook definition of cardinality estimation. So I'm glad you missed it, because I didn't want to be corrected. Okay, but there is nothing controversial here. So cardinality estimation is notoriously hard. I would also claim that there is no rigorous definition of the estimate. It's not a mathematical definition of estimate. So let me skip over this. And my biggest complaint, and not just mine, but this is what I heard people saying, is that it's unclear how to combine multiple possible ways to estimate the cardinality of a query output. There is actually a beautiful paper from about 20 years ago from IBM Research discussing the fact that if you have two-dimensional histograms, actually this hurts you. Because if you have two-dimensional histograms on the attributes A, B, and separately on the attributes A, C, and now you have a predicate that uses all three, that have a condition on all three attributes A, B, and C. You have two ways to combine these, and it's not clear how to take it and how to use these independent, separate results. Okay. So today we will not talk about cardinality estimation, but instead we will talk about an upper bound, a guaranteed upper bound on the query, on the output of the query. So formally, we will give as before statistics on the input database T, and most of the lecture will have these statistics restricted to the cardinalities. But later we will discuss also degrees towards the end when we get here. But you can also consider a number of distinct values. It's still a cardinality. We can use it there. And our goal is to come up with a number or a formula, a bound, such that for any database that satisfies these statistics, the output size is less than or equal to this boundary. So you can choose B to be infinity, but this is not very informative. We want B to be as tight as possible. And tight means that ideally we should be able to find a database that satisfies those statistics for which the size of the query is equal to B. We will not be exactly equal, we will be within a small constant factor of B. Okay, quizzes. So here is an example. Suppose all you know about these three relations are their cardinalities, and they are less than this red n. How big can the size of a joint be in terms of n? What do you think, Grace?
I've already seen this, it wouldn't be fair.
Sorry?
I said, I've already seen this, it wouldn't be fair.
Then you're not allowed to answer. Who doesn't know? Who knows? Yes? N squared, perfect. But database systems people will object. It's almost a case that you join on a key foreign key. If I tell you that Y is a key in S, how big is the result? It's N. Very good. Makes a huge difference, the information that's a key. So we will set this aside. For most of this lecture, we will not consider keys, but towards the end, I will show you how to add keys. Okay, another one. Here is an interesting one. So no keys, no assumption about keys. Every relation has sides n. It's a chain of length 3. How large can the output size be? This makes you think a little bit. How large can the output size be? I guess. Grace, you haven't seen this. Yes.
And cubes?
And cube is a good choice, yeah, because there are 3 relations. Why not multiply them? But the answer is actually just n squared. Do you see why? Because you can cover all 3 variables with these 2 atoms. So the size of the output cannot be bigger than the Cartesian product of R and T, because these cover all the variables. So an edge cover plays an important role. Okay, so the size cannot be bigger than n squared. What about a triangle? So here we're looking for triangles X, Y, Z coming from the 3 relations R, S, and T. What would the cover give us here? So it gives us n squared, right? Because we can cover all 3 variables with any of these 2 relations. But it turns out that we can use a fractional edge cover. And the fractional edge cover covers each atom with 1/2. And then the maximum size is n to the power 3/2. This is the AGM bound. This is why it's so fascinating. This is what we are going to discuss. Okay, so let's discuss it. So the statement of the AGM bound, and then I will show you both proofs, both of the upper bound and why this is tight, the proof of the lower bound. So we need to talk about fractional edge covers. Most of you know this. As usual, we associate to the conjunctive query a hypergraph. In the case of the triangle, the hypergraph is a standard graph. And here comes the definition. A fractional edge cover of a hypergraph or of a conjunctive query is a tuple of non-negative numbers, one for each edge, for each hyperedge or for each atom, such that for every node, for every variable, the sum of the weights of all the hyperedges that contain that node is greater than or equal to 1. So for example, in the case of the triangle, one fractional edge cover is to place 1/2 on each of these edges. Yes.
Why are you putting weights on the edges and not on the vertices? Because it feels like
That's a different notion. It's called a fractional vertex cover that also plays a role in a different place. In this case, the reason we put the weights on the edges is because, remember, a cover played a role. Once we choose an integral cover that contains all the variables, that gives us an upper bound on the query. Now, if I cover both the XY edge and the YZ edge, I can ignore the third one, and the size of the cardinality of the output is less than or equal to n squared. Okay, good. So some examples. What kind of edge cover would you put on each of these 3 graphs? The first one is a 5-cycle. That's easy. The second one, I struggled to draw this. I can't draw it. Here is the query. It's called the Loomis-Whitney query. It has 4 variables. And for each subset of 3 variables, there is a hyperedge. This is what I'm trying to show here. And your goal is to find any interesting fractional edge cover. And the last one is a 4-cycle. So what about the 5-cycle? What kind of, yes, Joe?
Can I ask a naive question? I may be the only one lost, but not that I'm representing somebody. The previous slide, even, I don't know what the rules of the game are. I can make the edge cover greater than one trivially by
Yep.
throwing ones all over the screen or tens or hundreds.
Minimum edge cover.
So what are we trying to optimize? What are we doing? Lost.
We are not trying to optimize, but you're absolutely right. There are many fractional edge covers. In mathematics and theoretical computer science, you usually will see the goal to minimize the sum of all these weights. That's called the minimal fractional edge cover or the optimal fractional edge cover. It turns out we don't always look for that, and we will see why. But that is a good possible goal to keep in mind. But keep in mind there are many, and that's what I want to illustrate. Let's see the many ones. Let's choose one for the pentagon. What would you put on the edges? What would you like to put on the edges of the pentagon to make it a fractional edge cover?
Would it be valid to put one fifth on all the edges?
If I put 1/5, is that good? Remember, each variable, each node must be covered once, at least once.
1/2.
And we need to put 1/2. Yeah. So this is what we need to do. What about Loomis-Whitney? Here,
1/3.
1/3. Beautiful. Okay. What about the cycle?
1/2.
1/2. But this is not what I did. I put 1 and 0. It's my choice. But you can argue that also if this is what you do, you can also put 0, 1. So what happened to the 1/2? Well, the 1/2 is a convex combination of the 1 zeros and the 0 1s. And it turns out if it's a convex combination, we don't care about that. It's not going to give us more information than the 2 halves. There is a technical term for this. A vertex of the edge covering polytope. The edge covering polytope are all the fractional edge covers. And the vertex is one that is not below a convex combination of others. Yes,
Is this like polytope in the LP pencil polytope, where we're looking at a vertex of the LP?
yes. That's exactly what a fractional edge cover is. It's a polytope. Yes, Joe.
No.
Okay.
What does convex mean here?
Convex, you take 2 points, like two fractional edge covers, like this 1 0 1 0 and 0 1 0 1, and you take a linear combination where the weights sum up to 1. If I take this plus this, add them up, divide by 2, that gives me 1/2. Yes.
A naive question. The dimensionality of this polytope is the number of terms or the number of vertices?
The polytope lives in R to the power number of hyperedges. The dimensionality of the polytope, yeah.
The number of numbers that we put on the screen. Yeah?
Exactly, number of numbers. So in this case, it would be R to the power 4. Okay, so here is then the IGM bound, this beautiful bound introduced by Atserias, Groche, and Marx, 2013. It was actually introduced earlier by Groche and Marx, but this is where they actually consolidated it and they proved other things. Take any conjunctive query, take any fractional edge cover. The size of the output of the query on any database is bounded by the product of these relation sizes to the power the weight of the fractional edge cover. Yeah, this is exactly what we observe for integral edge covers, and it generalizes for fractional edge covers. Moreover, this bound is not ridiculously bad. It's not infinity, but it is tight, in the sense that we can actually find a database, maybe different from our input, but one that has the same upper bounds on the sizes of the relations, on which the query output is almost as big as the minimum over all possible fractional edge covers. So here we are getting back to Joe's observation. There are many fractional edge covers. Which one do we care about? Well, we care about that minimizes this product. Since all of them are an upper bound, we want the smallest upper bound. Okay, yes,
So this, the lower bound is like constructive.
this lower bound will be constructed. I will describe the concrete database. It's a very boring one. I should warn you. It's a product, Cartesian product database, but it's very instructive to know it. Okay, so our triangle query looks like this. The triangle has many fractional edge covers, in fact, infinitely many. It turns out we only care about the vertices of the fractional edge covering polytope, and there are four. There are kind of the four extreme fractional edge covers: the 1/2, 1, 1, 0, 1, 0, 1, and 0, 0, 0, 1, 1. And the size of the query is bounded by the minimum of these three quantities. So here it's useful to reflect a little bit. It's not always the case that the smart formula, the square root of their product, is the best one. It could be the case that T is huge, the third relation is huge, and then the bound is simply given by the Cartesian product of R and S. Yeah, so we need to take the minimum of these formulas, which means that when we prove tightness, this minimum will be important. Okay, beautiful formula. And we only need to consider the vertices of the edge covering polytope. I will let you think at home. Why? Why don't we need to consider those that are convex combination? Do you know why?
No, I have a question.
Okay, good. Please.
So what edge does the Cartesian product of R and S correspond to in the triangle?
Just R and S, this one?
Yeah, I assume that corresponds to an edge covering.
Yeah, to cover, put a 1 on R, put a 1 on S, and put a 0 on T.
Okay, yes, I see. Because R and S's are our edges. Okay, cool.
R and S are edges, yeah. Yes, Joe.
It's another naive question. So I envision, just as Tyler was illustrating, the idea that we could take R and S from the cross product of lookups. We can do that with RT, we can do it with S and T. What does it mean to take half of R, S, and T? What's the intuition and how do you answer the question, the query?
I can't offer anything else than just say it's so beautiful. But work for integral edge covers also happens to work on fractional ones. I think it's beautiful. This is why I love mathematics. Sometimes they have these, brings you these very interesting insights. Yes, you had a question.
Yeah, if you try to like compute the minimum in the expression for the lower bound.
Yeah.
Isn't that like the equivalent to minimizing the exponent if you take each Ri to be like log Ri, and then you have this linear form Wi times log Ri.
So you want to apply the logarithm and then get more insight on that. That's exactly what we will do. We will apply the logarithm. But in the end, these are four numbers. You need to take the minimum. There is nothing else to gain.
Right, but like if you imagine a polytope, which is this like LP that you're trying to solve, and then what you're trying to minimize is just the optimization, which is a line. And so it feels that the optimal will have to be any vertex of this polytope.
Yes.
You can solve without looking over all the vertices.
You're answering this question here.
Yeah.
Yeah. Your intuition is perfect. Absolutely. A quick way to see this is indeed if you take the logarithm of two points in the polytope, then any convex combination is on a line, and therefore the maximum value on this line is going to be dominated by one of the extremes, and that's how you prove it. Any more questions about this slide? Because I have so many other cool things to show you, namely the proof. The proof of the upper bound is interesting because it uses information inequalities, a mind-boggling, fascinating topic, and there is a small community of mathematicians who work on this, and they are excited that this has application in databases. The other application is in secret sharing. The mathematics is mind-boggling there. There are lots of open questions. And then I want to show you the lower bound, the matching database, which is, I find it very insightful for us database people. It allows you to think quickly about what is a bad database that produces a big output. Okay, so let's start with the first one, information inequalities. So proof of the upper bound. So I need to talk about entropies and entropic vectors. We have a finite probability space. So there is a finite set D and a function from D to 0, 1, such that its sum is equal to 1. This defines a random variable. I call it X. Its outcomes are B, and is given by this probability P. The entropy of the random variable X is this expression, sum of the probabilities times log of the probabilities, put a minus sign in front of it. Is there anyone who has not seen this formula before? You have not seen it, okay. You need to look at it. I'm not sure what to say. The good news is that we will quickly move away from this expression to something that is actually much simpler. The first thing that we need to do is to recap the fact that the entropy satisfies the following inequalities. If the number of possible outcomes of our probability space is n, then the entropy is upper bounded by log n. It's always greater than or equal to 0. When is it equal to log n? People should know this. When is the entropy exactly equal to log of the size of the domain? Yes?
Guess that when the distribution is uniform.
When the distribution is uniform, this is when the entropy is maximum. You know less. When is it 0? When is the entropy 0? Yes?
There's only one possible outcome.
When there's only one possible outcome, there is no probability left. You know exactly what the outcome will be. That is when the entropy is 0. Okay. I just noticed here. Okay, good. So the good news, so you know from machine learning that there is a lot of usage of entropy in various applications. We will have a different view. We are going to look at an entropic vector. More precisely, our space here will actually be a table. We'll have multiple variables, x1, xn, and there is a joint distribution. And the entropies of various subsets of these variables defines a vector with 2 to the n dimensions, one representing the entropy of each subset of variables. Okay, so here is an example, and we will this goes towards in the direction in which we want to go. Imagine that we have a table, a relation. In this case, it's with 2 variables, x and y. And one thing we will often do, we will associate the uniform distribution on the tuples of this relation. Each tuple is chosen with probability 1/4. Then the entropy of the joint distribution of x, y is log of 4. But this is just one entropy. We will always consider the entropies of all the subsets of variables, of just x, just y, and the empty set as well. Why not? It's just a subset. The entropy of x is the entropy of the marginal. The marginal is no longer uniform. Yeah. So we cannot say that h of x is equal to log 2 because there are 2 values in x, but it is less than or equal to log 2. It cannot never exceed log of the number of distinct values in x. And similarly for y, and for the empty set, the entropy is always 0. That's how we will think about entropies. It is this vector. And the thing we are going to do with this vector is we are going to consider inequalities. And the inequalities that everybody should know are the basic Shannon inequalities. And here they are. The entropy of the empty set of variables is 0. the entropy of a union of two jointly distributed variables can only be bigger than the entropy of one of them. And the last one is actually the most important one. It says that the entropy is submodular. The entropy of a set plus the entropy of another set is greater than or equal to the entropy of their union plus the entropy of the intersection. These are called the Shannon basic inequalities, or Shannon's basic inequalities. Any consequence of these inequalities is called the Shannon entropic inequality, or a Shannon information inequality. And there are a lot of fun to derive. Okay, how many people did not know Shannon's inequalities? Oh, okay. The good news is you only need to remember the last one, submodularity. And let me show you. Yes.
So are U and V here random variables or are they sets?
They are sets of random variables.
Okay.
Think about X, Y, Z, and X, Y. Here is an example, and then it's going to become clear. We have three random variables, X, Y, Z, and I want to prove that this is a Shannon inequality. The entropy of just X and Y, XY plus that of YZ plus XZ greater than or equal to 2XYZ. It's called Scherer's inequality. So let's prove it. The way we prove it, we start from the left. We always apply submodularity. This is all we do. So what do we do? Choose two terms, and this sum is greater than the h of the union plus h of the intersection. Union is XYZ, intersection is Y. Okay, so what do we do now? Apply submodularity. So we choose two new terms, and we apply submodularity. And we get, again, h of XYZ and h of the empty set. So we got what we wanted, plus some extra terms. In this case, this extra term is 0. In general, the extra term can be anything positive because the entropy is positive. So we are done. Okay, so yeah, I let you contemplate it. It's a beautiful proof. So here is an important observation. It will play a role in a couple of slides. Notice that when we started, the variable x occurred twice. I'd like to say that x is covered twice. As we apply some modularity, this is an invariant. X continues to be covered twice until the very end. X is always covered twice. Same for Y, same for Z. Okay, good. So let's prove the AGM bound, the upper bound. We need to prove that for every fractional edge cover, the size of the query is bounded by that expression. And I'm going to illustrate on the triangle example. And the general case will be straightforward. I should mention this is part one, because in the first part, my goal is to connect databases and cardinalities in the query to an entropic vector. Yeah, and then we will focus on part two, which is the inequality of the entropic vector. So we want to prove that the number of triangles is upper bounded by the product of the cardinalities to the power 1/2. Here is what we do. We consider a concrete instance and imagine computing the query. So compute all the triangles that we have on that concrete instance, which is Q of D. This is a table with three variables, with X, Y, and Z. We don't know how big it is, but no matter how big it is, we're going to define the uniform distribution on its tuples. Okay, and H is its entropy. So H is the entropy of X, Y, Z, and of course it will have marginals, so we have a full vector of 8 entropic values.
Yes.
Yes.
So notation, when you say it's uniform, that's for the tuples that are in the output, and it's 0 for the ones that are not. Is that right?
Yes. Yeah. So I don't even think about tuples which are not in the output. Yeah. It just takes the tuples in the table. Okay. So here is this is the only connection between databases and entropys. Very simple. Log of the size of the relation R is greater than or equal to the entropy of the marginal xy, to the entropy of xy. Why is that? Well, remember that we defined our probability on the set of triangles. The relation xy, the relation R, will contain all the xy pairs of the triangles, perhaps even more. And as we compute the marginal, remember that the distribution is no longer uniform, but we don't care. The entropy can only shrink because it's maximum and the distribution is uniform. But all I'm saying is that what we had a couple of slides ago continues to hold. Log of the domain, the size of the support is greater than or equal to the entropy of the variable without support. Yes?
So what does XY mean, like notationally?
XY means the joint random variable whose outcomes are the values of X and Y. Okay, this is important. So let me go back and make this clear, because we have this picture here. In our case, we have three variables, X, Y, and Z. But if we just have two variables, then this is what you take. You take the outcomes are tuples of X and Y.
So then in the Shannon inequality, oh, sorry.
No, please continue.
In the Shannon inequalities, when we union XY and YZ, or yeah, and YZ, why does that give us XYZ? Because like back two slides. Like here, why does the union of XY and YZ become an XYZ?
This is a non-trivial question. And this goes back to Shannon's inequalities. The question is, why is it the case that if I take the entropy of XY plus the entropy of YZ, this is greater than,
Or I'm asking like syntactically, why is XY union YZ equal to XYZ?
Because I forgot to mention a classical abbreviation that we do in databases. XY means the set consisting of X and Y.
Okay.
And XYZ means a set consisting of X and Y and Z. We use this always when you talk about functional dependencies.
But then we're saying that the set, why does the set of random variables XY equal like sort of this join thing that's the XY table? Because that's where my disconnect is.
It's just not, these are different things. When I write here H of XY, I refer to these names, but the entropy is given by this complicated formula, but it applies to the distribution that I get from that table.
Mm-hmm.
Actually, why is that a vector? I'm a bit confused. So why is H a vector?
One component, second, third, and fourth.
Oh, so the vector is composed of like all possible marginalizations.
Mm-hmm.
Okay, so this XY here is not quite the same XY as the other on, is this exact same XY as the one on the Shannon inequality page?
Yep.
Okay.
And there was a question here.
Yeah, I think maybe the confusion I also kind of understood is on the, if you go to the current example we're looking at, the triangle one, like you define
This one?
the actual, for example.
Okay, the pool.
Yeah. So like P is defined on Q of D. But when you write H of XY, you're actually kind of like marginalizing over the missing column. So that's kind of what that is a shorthand for.
Exactly. That's exactly what happens. So the entropy is defined on all the triangles on X, Y, and Z. But now I can marginalize. This is a game I'm playing. So whenever I have an entropy of X, Y, Z, I consider the vector with 8 to the 3 dimensions. And I can talk about the entropy of XY, the entropy of X, and so on. Yes, Joe.
I find it useful to just think of writing out the discrete probability tables for the joins, and then there are these marginals, and we just multiply, right? The numbers pop out, right? The join processing becomes matrix multiplication or marginalization, depending what direction you go. Yeah.
But you don't go from the tables we don't start from anything here. Our starting point is the output. So if you're saying that you're multiplying something here, this is not it's not what happens here. I should have drawn, because I had a picture of with this example. Yes, thank you. So let me draw here so people on Zoom can see. So the way to think about this is that I don't care about what the input database is. I care about what the output is. And the output is a set of triangles. So think of them as ABC, ABD, FBD, and so on, many triangles. I don't know how many, but I'm going to define on this output, which I want to study, I'm going to define the uniform distribution. So each of them gets a probability 1 by n. And this defines an entropic function over the variables x, y, z. So what can we say about the entropic function of x, y? Well, it's going to be the entropic function of the marginal of x, y, and this is a subset of the relation R. So h of x, y, this is where I'm heading, h of x, y is less than or equal to the logarithm of R. Okay, our input relation, which for which all I know is cardinality. What I find interesting is the probability space that we are considering here, which is that on the output, is exactly different. It's exactly different. It's different from what is typically done in cardinality estimation. In cardinality estimation, we have a probability distribution on the tables, and we try to reason about the output. But here we start with the probability distribution on the output.
Thank you. That was extremely helpful. So this is a rather loose bound then, in some sense, right? This is a rather loose bound because you don't know how many zeros there were from the input to the output yet.
Yes, although it will turn out it's actually tight.
You can think of it like it's horrible. Think of it like an outer product. You can make like an you can cover an entire matrix just as they're using like two matrices with very few non-zero, an outer product like thing. That's the worst case. You can kind of like manufacture that topological example.
Okay, good. So everybody now agrees with this inequality. All I'm saying is that there is this connection between the input database, the size of the input database, and these three components of my entropic vector. Good. So what do we do with these? Well, we have proven that this sum is greater than 2h of x, y, z. And here is where we use the fact that we have started with a uniform distribution. So this is actually equal to the log of the number of triangles. It's equal to the log of this table here. Okay, and that's it. This so now from this, which means that the product of these three is greater than the square of q of t, which is exactly the formula that we were after. This principle generalizes whenever we want to prove that, we are given a general conjunctive query, and we want to prove the AGM bound that this inequality holds for any fractional edge cover. What we do, we apply logarithm to this left side. We will get a weighted sum, pretty much like we had here. That weighted sum is greater than the weighted sum of the corresponding entropic values. So all that remains to show is that that weighted sum of the entropic values is greater than or equal to h of all the variables x, all the variables in the query output. Yeah, this is still to be done. We have shown this for the triangle query, but now we need to prove that this holds in general for any fractional edge cover W. And once we have this, then h of x is log of the size of the query, and we are done. Okay, so this justifies looking deeper into this entropic inequality. And I know this is all new for you, but I will show you something super cool. How to prove this general entropic inequality. It's a generalization of Scherer's inequality. And it says that if these W's, if they form a fractional edge cover of the hypergraph consisting of these sets of variables y, then this inequality is a Shannon inequality. We can prove it using some modularity inequalities.
Sorry, can you say that again?
So the statement is that for any fractional edge cover W1, Wm, this inequality here is a Shannon inequality. Okay, so let's prove it. First thing I want to do is I want to convert these W's, which are rationals. I want to convert them to integers. And this means that I need to multiply with the least common multiplier, and I get a number on the right hand side. And now all the coefficients here are integers. Since initially the W's formed a fractional edge cover, for each variable, the sum of the W's that contains that variable is greater than 1. Now what happens is that each variable will be covered at least k0 times. Remember in the triangle query, we said that each variable like x occurs twice. Now each variable like x or y or z or whatever will occur at least k0 times. Okay, so how do we prove an inequality? We apply submodularity. So this is a beautiful proof from Barister and Bolobash. And they showed all you need to do is to repeatedly apply the submodularity rule. Take two terms from the left, replace them with a union and intersection. Okay. 3 observations. Observation number 1, each variable continues to be covered k0 times. We never lose a variable on the way. Observation number 2, this is on the homework. As you replace two sets with their union and intersection, the sum of the squares of their cardinalities strictly increases. Yeah, so what this means that if this has 2 variables, it has 2 variables. Now we have 3 variables in one. The sum of the squares, 2 square plus 2 square, will be strictly less than 3 square plus 1 square. So we always make progress with these submodularity applications. But we can't go on forever. This sum cannot increase forever. So when do we stop? What can go wrong? What forces us to stop? And it's a little bit subtle. We stop when these set of variables that we have here after this processing, if they form in a chain. And what happens is that if one of these sets contains the other, then the union and intersection are exactly the same sets. There is no progress. Yes?
Why do we need to multiply by k0? Like, why can't we just deal with fractional?
You can, but then you have to worry about how do you apply 1 unit of this rewrite. You need to take a fraction of this unit. Yeah, just I prefer to use integers. I think the original paper also used integers. Okay, so we apply the submodularity until these sets they form a chain. Once they form a chain, we know that every variable is covered k0 times. And the first element in this chain, y1, is the only one that contains all the variables. So its coefficient better be at least k0, and we are done. Okay, if you lost something on the way, it's not super important. I find this a beautiful proof. This Scherer's inequality has been proven and reproven in so many ways. Only accepts the most elegant proofs. There are alternative proofs that are, but, you know, if it's too complicated, put it aside. I find this one of the most elegant ones. Yes, Joe.
Yeah, you emphasize multiple times the coverage being maintained, and I don't understand why we care.
We care because at the very end, we get an expression like this, not the original one, a different one. And we want to show that this expression actually contains this term.
So it's to maintain the inequality.
To maintain,
Simple as that.
no, we will always decrease this because we apply some modularity. But at the end, we want to show that we have reached this term here. And the way we show this is by observing that since now we have a chain, the larger set will have some own variables that do not occur anywhere else. So there is some variable that occurs in Y1 here, which does not occur in Y2. That has to be covered K times, K0 times. Who can cover it? Only Y1. Because this is the only place where it occurs. And therefore, the coefficient that we get from here, therefore, not only is it the case that Y1 is equal to all the variables, which is also something we get from the coverage, but also the coefficient K1 must be greater than or equal to K0. It's a beautiful, beautiful argument. Good, cool. So, a discussion. So Scherer's inequality, it's so simple. These are special kind of information inequalities. And they are so simple because we can prove them by applying some modularity in any order. And it's more than this. We don't even have to worry about some modularity. You might wonder why did I waste time? Because a fractional edge cover is all you need. Scherer's inequalities correspond in one-to-one to fractional edge covers. If you have a fractional edge cover, that gives you a Scherer inequality. If that inequality holds, then the W's better be a fractional edge cover. It's an easy proof. Okay, as a consequence, any such inequality is an upper bound on the query. And of course, the AGM bound takes the best fractional edge cover. We get many of them, but we want the smallest bound. The next task is to prove that the AGM bound is tight. That smallest bound that we can obtain is actually a mathematical formula that can be reached by a concrete database that we construct. Okay, and that database, I think it's interesting. For database practitioners, I find that an interesting message, how to construct the worst case database. That's proof of the lower bound. Okay, I'm going to prove it by example only. I'm going to use this example with the triangle query. And recall that the AGM bound is a minimum of all the fractional edge covers. And now I'm calling them WR, WS, WT, because it's very important to keep track where they come from. I should have mentioned here an important point. For this proof, for the lower bound, I'm giving up on entropies and entropic inequalities. I only retain the fact that the bound is given by a fractional edge cover. Now, the proof of that upper bound was using entropies, but now all I care about is that this is a fractional edge cover. Okay, so how do we minimize this expression? Like your colleague said earlier, we apply logarithm. And then finding this minimal value boils down to solving a linear optimization problem. What is a linear optimization problem? We need to minimize this weighted sum. This is exactly this logarithm, subject to the fact that the W's, they form a fractional edge cover. And this is just a linear set of constraints, fractional edge cover. For every linear optimization problem, there is a dual. There is a dual problem. How many people here know how to construct a dual given a linear optimization? Not that many. So like, you have lots of new stuff in this lecture. Here is how you construct a dual. It's a fantastic. You have to learn this. It's a fantastic thing. Each of these constraints is a linear inequality. In the dual, you create a new variable for every column. So, sorry, what am I saying? It's wrong. In the dual, you create a new variable for each constraint. So there will be a variable for the constraint, which I called X, a variable for constraint Y, one for constraint Z. The constraints will correspond to the columns. So the sums that you see here are exactly the columns. And the right-hand side of the constraints are the coefficients that we get from here. This is how you construct the dual. And the optimization, optimization objective is a linear combination of those variables whose coefficients are the old constraints. That was a mouthful, so I can't do it justice. There is a simple way to construct from the primer to construct a dual program. And the strong duality theorem states, the weak duality theorem states that for every feasible solution, this objective value is greater than or equal to this objective value for every feasible solution here. So we always have left greater than or equal to the right. The strong duality proves that at optimality, when you have minimized the left and you have maximized the right, these two values are equal. Beautiful, beautiful stuff. Good. So my AGM bound, I can think of it as a maximum value that I can obtain by solving this linear system, which is like a fractional a vertex packing, or like a fractional independent set. Okay, we'll get back to the independent set. But now I want to finish the proof. Here is how we use the optimal solution, or in fact any solution of the dual program to construct a database. For each of these values, which are associated to the variables of the original query, to X and Y and Z, to each of them, we associate a domain, which is 2 to that power, 2 to the Vx, 2 to the Vy, 2 to the Vz. I should correct myself. The domain is not the number, but it is the set of numbers 1 to 3 up to that value, 2 to the power Vx. Now, to be rigorous, I needed to take here the floor because Vx is some fractional and 2 to the Vx might not mean integer. Okay. And now the database is a product database. The relation R will be the cross product, the Cartesian product of the two domains of the variables X and Y. The relation R is a cross product of the Y's and Z's, and similarly for T. Okay. Quick question. My database, does this worst case instance database, does it satisfy, is a cardinality of R upper bounded by this number that I started from, the cardinality of my true database? Is a cardinality of R star less than or equal to the cardinality of R? I need to backtrack a little bit here. We don't have the input database. What we have instead are these three numbers, R, S, and T. And maybe I should have used here some notations like N1, N2, and 3. There is no R, S, and T. It's just their numbers. I'm looking for a database whose cardinalities are not bigger than these numbers, and for which the query output is as big as this AGM bound. This is what I'm doing. And my question to you is, this database I just constructed, does it satisfy that cardinality constraint? Is the cardinality of R star less than or equal to my original number. And why is that? Well, because cardinality of R star is the product of these two. When you take the product of these two domains, the size is 2 to the power Vx plus Vy, and Vx plus Vy is less than log of my number. So here we go. The cardinality is done. What about the query output? Well, since everything is a Cartesian product, all combinations of values of the variables forms a valid output. And therefore, the size, the output of the query is going to be the product of these three, which is not exactly 2 to their sum, to the power of their sum, because of the rounding. The rounding is what prevents us. But the rounding can only create an error of a factor of 2. So I put here a 1/8. Okay. Now look at the exponent here. This is exactly the objective of the dual program. So this is going to be equal at optimality with the objective of the primal program, which is my AGM bound. And this is what I'm getting. This is when I might choose the optimal values. This is exactly 1/8, 2 to this power, which is exactly, oops, no more 2. This should be exactly the AGM bound, no more 2 to the power. Okay, that was a proof. I let you contemplate this at home. Let's have some fun. I have examples. And get most of the fun when all the cardinalities are equal. And when all cardinalities are equal, then we can actually use a correct notion of a fractional vertex packing, which, given a hypergraph, a fractional vertex packing is defined as a set of numbers associated to the nodes of the hypergraph, such that for every edge, the sum of the weights of the nodes for that edge is less than or equal to 1. Now, getting back to our previous construction, the constraints that we had a log, will have a log n everywhere because our cardinalities are equal to n. So the trick we are going to do is we are going to take away the log n and have the simpler constraints, which means that B form a fractional vertex packing, and we need to remember to multiply with log n later on. Okay. Long story short, the optimal the product database for the triangle is going to look like this. Don't worry too much. I have some simple examples. So let's play some game here. Here is one of the queries that we discussed earlier. It's a simple chain query. If all the cardinalities are n, how big can the output be? What is the maximum size of this query? N squared. Let's derive this. Let's construct a project database for which the size is n squared. So here is how to think about this. Here is a graph. The fractional edge cover is on the top. It's not fractional, it's actually integral. It's 1, 0, 1. You can't do any better. The fractional vertex packing is written at the bottom. So remember, we cannot exceed 1 for any edge. So I placed a 1, 0, then 0. I placed the 1, 0 here, but I can't increase this. You can't increase it. And this is optimal because look, they're equal. At optimality, the sum of the green values must be equal to the sum of the red values, and we are there. You construct the worst case instance by reading from the fractional vertex packing. And here it is. The relation R will be the product of n to the power 1 and n to the power 0. N to the power 0 is just 1. The relation S, well, S is kind of the stepchild here. It's getting 1 and 1. S is very small. And T is 1 times n. Okay. What about this one? What is the maximum size of this query? It's a chain. how many do you need to pack? To cover, sorry. 3. We need 3 to cover. So here are my 3. I placed 2 ones here. You can do other things as well. And this is an optimal fractional vertex packing. So from here, you can immediately see the worst case instance.
This is basically just the outer product, right?
The what?
An outer product. If you think of R
Uh-huh.
as R, S, and T as vectors.
Yes.
This is basically saying your biggest output is just made by making a dense matrix.
Mhm.
You feed in like a vector or like a row vector multiplied by a single scalar multiplied by like column vector. Or no, the other way around, sorry.
Yeah, I'm sure you see this much better than I see it, but yeah, but I agree. There is a matrix or a tensor interpretation here, which is very elegant. Yes.
The number is where you have the cardinality of all the relations, but in the example, actually has one, right?
Who has one tuple?
Like, example is setting up with the cardinality of all the relations.
Yes. I meant to write it, but I forgot. Thanks for asking. So usually the mathematical setting is nicer if you put here less than or equal.
Okay.
If you insist in equal to n, no big deal. Can you construct a database where all 3 have size n, and still the size is whatever it needs to be, n squared? How do you do this? Just put into S some junk tuples, whatever you want to put there, and increase it to size n. Yes?
Can you generalize this like machinery to work on constraints that say, for example, that R and S and T are the same like exact tuples? Like, because I'm thinking of like a graph where the 3 relations are the same.
Yes, I got it. It's also a very good point. Especially for triangles, we should take the same one. So if I want this to be the same relation, R, the trick to play there is that you start from these definitions, and then you take R to be their disjoint union. You make the domains of the variables x, y, and z disjoint. So they still will have size n and 1 and n, but there will be completely disjoint values. And then you stack them on top of each other. And when you join them now, you join R with R with R. The only tuples that join with those that you have designed to join. The price you're paying here is that your true relation R no longer will have size n, but can be 3 times bigger. And you need to account this, and there's another penalty to pay in that tightness assertion, in addition to the rounding error. Good, beautiful. So I still have 7 minutes to show you extensions, because I think it's good to not get stuck into the AGM bound, but to see the bigger picture as well. But before that, let's briefly summarize. So to keep in mind that the upper and lower bound of the AGM bound are given by the fractional edge cover and respectively fractional vertex packing. And their equality follows by the strong duality theorem, which everybody will check, right? We go and look in Wikipedia, strong duality of linear programs. The worst case instance of the AGM bound is a simple product database. This is what gives you the largest possible query output if all you know are the cardinalities. If you know more stuff, then it's no longer a product database. This is where it gets interesting. These are my extensions in the next 6 minutes. Notice that all our discussion applies only to full conjunctive queries. What happens if you want to project on some variables? And the answer is very boring. You just remove the other variables from your query, and you consider the restricted relations with fewer variables with the same cardinalities, compute the AGM bound, and that is still optimal. There is nothing else we can say about how a projection decreases in size. In the worst case, it can be as big as that of the original query. And finally, my main criticism is that it only applies, it only accounts for cardinalities. And that's where I'm heading next. 5 more minutes, yeah? So I do want to talk about extensions. Here is what we know how to handle today. So for the AGM bound, we can use cardinalities. And I didn't show this, but it's easy to see that if you have statistics on any of the projections of the base tables, you can just throw in these as entropic terms. You throw them in as atoms in your query, and this could improve your AGM bound. Yeah, if you know that some domains are very small. In addition, what we know how to handle, this is going to be the new thing, are maximum degrees. Remember, we discussed about average degree. This is what database systems use today. And I think it was you who complained why not use maximum degrees. That's what we're going to do now. We are going to use maximum degrees because we want to get upper bounds. And notice that the maximum degrees actually capture functional dependencies. A functional dependency holds if and only if the maximum degree is 0, not 0, 1. You need to apply logarithm later and then it's be 0. Yeah. And more, this is very recent work. We actually also know how to take into account when we have statistics on the LP norms of these degrees, which is, I find is super cool, but I'm not going to talk about this. I do want to talk about functional dependencies first. There is a hack, a trick, by which you can use the AGM bound without any new entropic inequalities to handle simple functional dependencies. And they're important. I remember for a join can have worst case size n squared, but it decreases to just n when we know that y is a key. Let's call a functional dependency simple if the left-hand side has a single variable, a single attribute. Now, if you know a bunch of functional dependencies on your query and all of them are simple, the following technique gives you a tight upper bound on the query output. What you do, you need to modify the query by replacing each atom with a new atom. I mean, it's going to be the same cardinality, but the attributes are extended to the closure of a set of attributes with respect to the given functional dependencies. And I'm looking at Max, and I don't think Max knows what the closure is.
So you're basically taking, for every FD, you go look in all of the tuples, and wherever they appear, you throw in the output.
You throw in additional things that you will follow from the FDs. Yes?
Doesn't this only not increase the atom size if the functional dependency is in a tuple that has arity 2? Like if S was Y, Z, U, then I'd have to put Z and U into R, right?
Yes.
Okay.
Yeah, and then you compute the AGM bound of this expanded query, and that's it. That's going to be a tight bound.
Sorry, what is Y plus? I'm a little lost.
So what I think Max described. So you start from the variables variables that occur in R. You look at all functional dependencies that on the left have something where U is in R. And then you simply add V.
We're like fusing the relations R and S in a sense.
It's not exactly fusing because somebody mentioned you might have additional attributes in S, but the functional dependency is only from Y to Z.
Yeah.
So then what you can imagine doing is that you take the unique value of C for each Y and you add it to R, and that will not increase the size. Yes.
This is just like a join, right?
It's like doing a join, and you know that the size of the join will not increase because of the functional dependency.
It's a lookup, which is the doesn't
Lookup.
fan out.
So this only works with the FD tuple?
It works all the time, but you will not be able to guarantee that this bound is tight, except where the case when it's simple. So let me show you how it works. So this was a triangle query. We never consider a functional dependency, but here is what happens if we have a functional dependency. These were our 4 fractional edge covers, and this was our old bound. But now if if I know that S dot Y is a key, then in the expanded query, I can add Z to R. Once I add Z to R, everything changes. And now I have much better edge covers. I can cover everything by just covering R. So I have this 1, 0, 0. And I can also, I still need to keep the other one, the 0, 1, 1. And then the bound increases to the minimum between R and S times T. S times T was here, but R was not here. Okay, so this technique always gives you an upper bound, but I'm invited to prove with an exercise. It's not part of the homework, and invited to prove with an exercise that if the functional dependencies were simple, you also get a lower bound. Good. So we are running out of time. I think it's a good time to stop. I strongly invite you to read the next 3 slides that show you a real example of an entropic inequality that proves an interesting upper bound on a query. We'll stop here. And on Thursday, Hank will describe a matching algorithm for the AGM bound. We only know it for the AGM bound. We kind of have some insights into how to extend it for the other inequalities, but I don't think Hank will talk about that. Good, cool. So thanks, folks. I'll see you on Thursday then. Okay.